My name is Martin Millon. I obtained my PhD at GPFL in 2021 before moving to the US at Stanford University as a postdoctoral researcher. And then I came back to Switzerland last year, first at ETH Zurich and now at the Department of Theoretical Physics of the University of Geneva, where I'm starting a new project as an Ambizione fellow funded by the Swiss National Fund. So I was always fascinated by space science and astrophysics and cosmology. So from the very young age, I had like a poster of galaxies on my walls. And during my studies, I was hesitating between engineering and fundamental research. So I even worked for 6 months as an engineer, but I switched back to academic research. I decided to study cosmology because it's a very fascinating field. Like in astrophysics, we study stars, planets, celestial bodies, but cosmology asks questions about the universe as a whole. Like we study questions like how fast the universe is expanding, why does it expand, how gravity is affecting the shape and the dynamics of the universe. So that's the fundamental question that I'm interested in. In cosmology, there is a big problem. Like the universe expansion rate that is predicted by the theory is slightly smaller than the value that we are actually measuring. So the expansion rate of the universe is known as a Hubble constant, and this problem is known as the Hubble tension. So the goal of my project is to get the precision, the measurement of the Hubble constant as precisely and accurately as possible, to make sure that there is no measurement error that could explain this discrepancy. And then if there is no measurement error, it means that we are missing something very fundamental about our understanding of the universe. We're not understanding very well the laws of gravity on such a big scale. My project started in 2025 and it will run for 4 years. So here at the Department of Theoretical Physics, I'm working with a PhD student, Harry Krisic, whom I met at ETH Zurich. And so we will be working on this measurement for the next 4 years. So the expected result would be either to find, as the theory predicts, or either to find a discrepant value. And if we are in the second case and find something not compatible with the theory, it means that we are missing something very fundamental about our understanding of the universe. We are not understanding how it expands, which means that we don't understand the forces that are at play. So it means that there's a potential for discovering new forces, new physics that are not included yet in our model. So to measure the Hubble constant, we're using gravitational lenses. So it's a phenomenon which appears when a foreground galaxy is in the front of a background one, and the light rays coming from the background galaxies are distorted by the foreground. And this effect allows us to measure the geometry of the universe and the Hubble constant. So I would like to thank my colleagues at the Department of Theoretical Physics and my collaborators worldwide who are working with me on that project, and also the Swiss National Fund for supporting my research. And I hope we will get the results we are expecting.